Hello, in today's video I'm going to talk about image analysis and more specifically how AI can be used to improve productivity. So I'm going to talk about AI in combination with Omnimet. So my name is Thomas Engdahl. I'm the founder of the company Bildanalyssystem and also the founder and one of the developers of the product Omnimet. I'm based in Stockholm in Sweden, and we are distributing this software worldwide using resellers. And two of our main resellers is Micron in Sweden and Bueller worldwide. So first of all, AI can be used for many things. And I'm going to start off with giving a few examples of what it can be used for. One example is super resolution. So by using AI, you can actually achieve a higher resolution using inexpensive equipment. So for example, this could be improving low resolution SEM images or removing artifacts and dust, scratches, uneven lighting, and so on. Another thing is to use it for classifying objects found in the image. You can classify defects, items, or other findings. In this case, the objects found are often marked with a box, and each box got a classification. And the third way of using AI is to classify each individual pixel in the image. This is called segmentation. So this can be used to detect virtually anything or something special in the image. For example, grain limits, an inclusion, nodules, ceramics, and defects, literally anything. And in this session, I'm going to focus on segmentation. So let's dive a little bit deeper into segmentation. So what is it? Well, it is basically transforming one image into a binary image. And in image analysis, we've been doing this for ages. But the traditional way of doing this is by the means of using thresholding, at least as a starting point. So you threshold brighter or darker areas, or perhaps based on color or hue in the image. And then you can combine that with a number of filters, often filters like fill holes, watershed for separation of objects, erode, delete, and there are literally hundreds of different filters. And this is actually quite hard to learn. So using AI, we replace this technology with just a simple use of a model. So the idea is that with the click of a button, convert the image into a binary image. So AI can be trained to perform far better than all the previous methods, and in many cases actually a lot better than humans, at least if you consider the time spent on doing this. So this segmentation is never used standalone. It's always used in combination with computation. So once you got this segmented image, you compute on the segmented image, and it could be literally anything, like a number of percentage of a given color, as in this case, or something different. And in Omnimet, we do this with the same traditional tools we've always been using: a grain size tool, a volume fraction tool, and there's a general object measure tool, and also the script engine where you can do a lot of things. So I'm not going to talk so much how you train a model, but very simply I'm going to introduce the idea. So basically what you do is you take an image or a set of images and you annotate the ground truth manually. Or if you like, you can go with the traditional way of doing a threshold and then do the adjustment manually. But it involves some manual laboring of annotating or editing the image. So For every image, there is a mask image or a ground truth image. And this could be one image, it could be 10 images, or it could be hundreds of images. The more the better. And depending on the problem, you might require roughly 30 images, or in some cases hundreds or even thousands of images. Anyway, you send these pairs of images into a training algorithm, and that will eventually create a model. And the model is actually just a plain file that can be downloaded to your computer, and it can be used. Just a note, training the model is very computer intensive, so it requires a high-end computer with a graphic board and a lot of memory. But using the model, I mean, you can take advantage of hardware, but it's not really required. So some examples. This is ceramic coating, or actually what we see is the binding layer between the substrate and the ceramic. So the ceramic layer is the gray in the bottom, and the binding layer, like the glue, is in the middle, and the substrate or the metal is in the top of the image. So by traditional means, doing thresholding here fails quite badly. Now this is an image with a lot of scratches and dust in it, so that is all detected. And the ceramic, the binding layer also got a lot of black holes, and that is not detected, which means if you try to measure the thickness of the red layer, you will actually measure a lot of other things, and in some cases the image is split into two, like here. Another example is measuring the ferrite percentage in duplex steel, which is clearly two different phases. The ferrite is the brighter and the austenite is the darker. And by thresholding the image, it obviously misses the interior of the austenite because it's virtually the same gray level as the ferrite. So you have to manually adjust this. But using AI is almost 100% perfect. And the algorithm performs much better. That's the second step, so to say, performs better. And grain sizing, that has always been a huge problem in metallurgy. And with traditional segmentation, it will fail unless you have an extremely clean and polished material with very visible boundaries in black. But that's rarely the case, and this is a typical example of what it can look like. So traditional segmentation will not work, and you have to rely on manual counting. While AI-assisted might actually work quite well, it will not be 100% perfect, but it's a lot better. So in this next step, I'm going to demonstrate with a live video how much time you can actually save by using AI. So let's start with a ceramic coating example. So in this case, we want to calculate the thickness of the binding layer. And in our case, we want to measure in 10 places for 10 images. That is a total of 100 measurements. And then out of that, we normally calculate the average, the min, and the max. So as I said, the binding layer is porous, so regular thresholding does not work. So if to do this the traditional way, we have to do it manually. So let's have a look at what that looks. So this is Omnimet, and I have a clock running. Unfortunately, start on 1 second, so forgive me about that. But let's just check how we do this manually. So we start off by just doing manual measurements, and I have sped up the video 4 times, but the clock is also ticking 4 times quicker. So we do this. Yeah, not 100% perfect, but it took 35 seconds, and if we extrapolate that to 10 images, it's roughly 3 minutes labor work. In this case, we achieved an average thickness of 112 microns. So that's how you do it manually. And let's compare with AI assisted. So in this case, I'm using a script and I'm trying to do this automatically. So we do the segmentation first and then we do a script to measure the segmented image. So this is going to be a little bit quicker. So pay attention. So I'll start the script, segment, measure. And now I actually move on to the second field of view, segment and measure. I can argue that the most time spent was actually moving the sample, which is quite interesting. But all in all, it took 10 seconds to do two images, which means 10 images takes roughly 50 seconds. And actually, we received the same result, 121 microns. And the difference is I actually counted 20 intercepts per image. I can do 40, 50, 100. It doesn't really matter because I do it automatically. So if to compare, when using 10 fields of view, which is our baseline, it takes 3 minutes compared to 50 seconds to do it manually versus AI assisted. That is a time saving of 75% or 4 times quicker if you like. And in this particular case, the precision was doubled. Let's move on to another example. And I was talking about this duplex steel. And in this case, we want to calculate the austenite percentage using a 10 by 10 grid, which is according to the ASTM E562 standard. And again, we want to measure more than one field of view. 10 field of view might be sufficient. The more the better. I'm just going to do 2. So this sample is also a little bit difficult because the brightness of the blue area is actually very close to the brightness of the ferrite. And the sample also got other defects. Let's see how this works doing it the traditional way. And this time I'm going to try thresholding, but it will require some manual adjustments. So let's run the video. So we do the thresholding. We need to manually adjust it to fit the image as good as possible. And then we apply the tool and it counts the intercepts between austenites and the grid points automatically. But in this case, we can adjust if there are errors. You can be lucky, you can be unlucky here, but there's a few errors and I click them manually. So let's do the same for the second image, and I have to adjust quite a few places. So that took 1 minute and 52 seconds, and for 10 images it will roughly take 9 minutes to do this. So let's try the same thing with AI. So in this case, I run the video, I do the segmentation, it's perfect, apply the same tool, do the same procedure for the second image, and there is no need for manual adjustment. So the total time spent here was 14 seconds, and for 10 images that would be 1 minute and 10 seconds. So a comparison again, 10 fields of view, manual measurements take 9 minutes, AI assisted 1 minute and 10 seconds. The time saving is a staggering 87% or 617% faster, which way you prefer to say it. So if you do 10 tests per day, each test is 10 images, this corresponds to time saving of 1 hour and 18 minutes. And that corresponds to 36 working days per year, assuming you work 200 days per year. That is quite a lot. And many labs do a lot more than 10 tests per day. So final example is the grain size, and grain size can be measured in so many different materials. And on the right hand side you see 3 different examples. I'm gonna try this on brass, and this is from a cartridge sleeve. And the problem with grains is in many material there are something called twins, which is interior or internal structure in the grain, and we're not supposed to count them, only the surrounding grain boundary. So normally with this standard you should count 10 fields of view, or actually 500 intercepts. So this is a very difficult task, but let's try it. So this is the brass material, and it will not work with traditional ways of thresholding. It's just impossible. So we have to do it manually. So in this case we put a line on the screen and we click on each boundary. And even this is difficult for a human being. But with some training you can do it. So I will speed up the video. Yeah, you see, I even go for 8 times the speed. This takes a lot of time. So now we have done 88 intercepts, and remember we are supposed to do 500. But I'm going to stop here. So the total time to do 1 field of view was 1 minute and 50 seconds. And observe in this case the result was 88 intercepts, and that corresponds to an ASTM value of 3.2. So let's do this again, but now AI assisted. So we segment the image and it will detect the boundaries. And now the grain size tool automatically detects the green line overlaid with the red. You can still manually adjust it. So it was so quick here. So, well, almost too quick. So in this case it took 13 seconds. And observe, we got the same result, 88 intercepts. So exactly the same result. A little bit of luck maybe, but obviously in the same domain or ballpark number. So if we compare this now again, and assuming 10 fields of view, the total time of doing this measurement manually is 18 minutes. And with the AI assisted, it's 2 minutes and 10 seconds. And this is a tricky sample. The time saving is 80%, or it's more than 5 times faster. So if you do this test 10 times per day, it corresponds to 2 hours and 40 minutes time saved each day, or 66 working days. And that is quite a lot. So to visualize the time consumption, manual versus AI, and obviously coating, there was a lot of time saving, duplex as well, and grain size even more. So summing up, AI offers huge time savings, as was proving in the videos. It also removes quite tedious and monotonous work. And it increases the precision, it increases the repeatability, and it also potentially decreases the human bias. Human manual measurement is always done in a way that it fits what you strive to find. It also decreases the variance between users. And it probably increases the consistency, especially if you measure high volumes. People get tired of doing this type of work, and eventually after an hour the precision goes down. So that's pretty much this video. If you found it interesting, we are looking for pilots, companies that want to participate in developing new models and evaluating this kind of technology. A beta version of the software is already available, and the final release is scheduled for November 2025. With that, I say thank you, and bye-bye.